Imagine having to drag such a heavy box across the room. It would make even the strongest of men cringe. Fortunately, there is an easier way. It's called the wheel. Ever since the prehistoric man has invented the wheel, it has revolutionized the ways man leads their life. It is difficult to imagine our lives without the wheel. It has applications in industry, agriculture, transportation, and almost every other aspect of human life. And at the heart of the wheel lies the concept of rolling. You must have a fair idea of what rolling motion looks like. Now let's take a closer look at the rolling motion of a bicycle wheel. At the first glance, everything looks normal. Now let's make things more interesting by taking a picture of the wheel.
Here we are. Now look at this picture carefully. Do you notice anything peculiar? No? Look at the upper half of the wheel. The spokes are blurred and difficult to distinguish. Now look at the lower half. The spokes are easily distinguishable and clearly visible. This means that at any instant of time, the upper spokes are moving at a velocity faster than the lower spokes.
Now you might have seen that when the fan is rotating at a slow speed, you can distinguish its blades. But when it is rotating at a higher speed, you cannot. How is it possible? Let's take a deeper look into this mystery by understanding rolling motion. Now when we speak about rolling motion, it must be understood that we are speaking about pure rolling.
Let us begin by defining the rolling motion of a disc. If the disc is rolling without slipping, then the point of contact of the disc with the surface is stationary at any instant of time. Rolling is a combination of rotation and translation. Since translational velocity of a system of particles is the velocity of its center of mass, the translational velocity of the disc is equal to the velocity of the geometric center of the disc. Let us name this point C and its velocity as Vc. Vc is parallel in direction to the surface. The rotational motion of the disc is through the axis at C. Now let us consider 3 points on the disc at P1, P2 and P3 as shown. P1 is the point of contact of the disc with the surface. P2 is the point diametrically opposite to the point of contact P1 at that instant. P3 is any point in the interior of the disc. Now each of these points on the disc has two components of velocity. One is the translational velocity Vc and the other is the linear velocity Vr due to the rotation of the disc. Now we know that for any point on the disc, Vr is equal to r omega, where omega is the angular velocity of the disc and r is the distance of the point from the center of the disc. The direction of Vr is perpendicular to the radius vector of the point with respect to C. Now for the point P3, the components of velocity Vr and Vc are shown. The resultant velocity vector can be called Vz. Note that Vz is perpendicular to P3, P1. Now, for the point P1 to be at rest, the linear velocity due to rotation should be exactly equal and opposite in direction to the translational velocity Vc. Now, the magnitudes of both Vr and Vc are equal to r omega, where r is the radius of the disc. On the other hand, at point P2, both VR and VC are in the same direction. Their magnitudes are also equal to r omega. So the velocity of the point P2 is equal to Vc plus Vr equals to r omega plus r omega equals to 2r omega equals to 2Vc. Hence the point P2 is moving at a velocity twice as fast as that of the center of mass. This velocity is directed parallel to the surface. Therefore, in pure rolling motion, the point which at any instant of time is diametrically opposite to the point of contact is always moving at a velocity twice that of the velocity of its center of mass and in a direction parallel to it. It can also be concluded that at any instant of time, as we move from the point of contact to the diametrically opposite point on the disk, the velocity increases from 0 to 2Vc, where Vc is the velocity of the center of mass of the disk. This condition applies to all rigid bodies which are rolling without slipping.
Let's get back to the bicycle wheel problem. It is now clear to us from the animation that points in the upper part of the wheel move at a faster velocity than those in the lower part of the wheel, which is why the spokes in the upper part are more blurred and those in the lower part are clearly seen.